Okay, so hello and welcome to this lecture on data analytics, data science, and artificial intelligence. Today we will be studying more about k-nearest neighbors and some validation functions and the like. So let's just dig in. So let's talk about something called k-nearest neighbor classifier. So this is a very simple classifier in the sense what you do is let's take a very small data set, okay? So let's take a data set where I will draw the x-axis. Just a second, if I can draw a line, that would be better. I think there is no provision to draw a line. Oh, there is actually, yeah. So if I draw a line, right, maybe something like this, and let's draw a line, okay. So let's draw a line like this, okay. Just a second, yeah, I think, yeah, let's draw a line, okay. I think I got the code. So let's say I draw the y-axis. Yeah, so let's draw the y-axis and let's draw the um, x-axis as well, right? Okay. Now let's draw some points. Let's say there are two classes in this data set, which means there are two different types of, okay, sorry. Yeah, okay. Yeah. So let's say there are two data sets of different two classes. It could be, let's take a very small example where your data set consists of the x-axis denotes the age and y-axis denotes the maybe the probability of, oh no, maybe y-axis denotes if the, let me just write this off, it denotes the whether the person has cancer or not. Okay. Okay. So the red class denotes that the person has cancer, and the green class denotes the person does not have cancer. So let's say if I just plot it like this, if I just plot a bunch of data points, okay, this class, and let's say I plot some points of the other class as well. Green denotes the person does not have cancer, while red denotes that the person has cancer, right? Now, if I ask you a very basic question, let's say if you take a point here, let's say this point is my test point. Okay. If I ask you a very basic question here, which class do you think this test point should belong to? By looking at the data, what can you say? Does it belong to the class red or does it belong to the class green? You might think and answer that, yeah, I think this will belong to the class green. Why? Because if you look at the uh, value, the test point, it is lying closer to the green points, right? So that is why I can say that this test point has a class green. But so that is actually, so each machine learning algorithm that we are studying, in this case today, k nearest neighbor, has some assumptions they make of the data set. The assumption that k nearest neighbor does is something very simple. K nearest neighbor says that data points that are close tend to have the same label. So the data points that are close to each other, they tend to have the same label. Now, if I take another test point, let's say this test point is, let me write it as x1. which is the test point that we already said. Let's say there is another test point, something like here. Let's say this is x2. Okay. Now over here, if I ask you which class do you think x2 should belong to? Should it belong to the red class or should it belong to the green class? Maybe if you can think that this thing is at a distance of this, and let's say this is the nearest point of x and red. Now there is like a confusion whether it should belong to the red class or the green class. So what I can do is, instead of just looking at 2 points, just looking at a single point, which is either the red one or the green one, maybe I can consider the two closest points. Okay. And this time we are only considering the two closest points. In that case, this one and this one are 2 points that are closer to the point x, and then I can say that this also belongs to the class red. But here initially, like for this point x1, it was very easy to say it belongs to class green, because you can just look at one point, which is, let's say, this point, that can tell you that the point belongs to class green. But when it comes to this point, you can say it either could be this one, or could be this one, or could be this one, could be anyone. But in that case, if I just take a more majority vote, in the sense if I take more number of points in consideration, then I can maybe better be able to make my prediction. So that is why I can say that for that I need to increase my value of the number of points I see. So for k nearest neighbors, the k denotes the number of points you are considering. Okay. So the algorithm is something very simple. So if I write the algorithm, okay, compute the distance of test point x with all the other points. Okay, which means let's say this denotes a distance vector, capital D, denotes each element of the distance vector denotes the distance between the point x and xi for all I belong to the data set, capital D. Okay, so let's not call it distance vector, let's not call it capital D. In fact, let's call it just a second. Yeah, let's call it small dist. Okay. Now to look at now what you do is you sort the distance vector in ascending order, which means the distance that is very closest to the point x will come at the top, and similarly you can look at the other one as well. Take the maximum top k elements from the distance vector. Distance k denotes the top k elements of the distance vector. Okay, and then do a majority vote, which means then last step is do a majority vote, which means if, let's say, my value of k is, let's say, 4 in this example, and my distance vector contains the distance of 4 contains, let's say if I write dist 4, let's say it contains 3 green points and 1 red point, right? Then in that scenario, your value that you will predict for this case is green because 3 are green points, right? So if you do the majority vote across distance k, then you take the green point in this scenario. One thing that you can ponder upon to understand it better is if you think through, what do you think is the behavior of the algorithm when the value of k is 1 and when the value of k is n, where n denotes the number of samples in the data set. For k equal to 1, you are just looking at the most closest point, just one point in that scenario. In that case, you might think that, okay, but in that case, the accuracy of the model will be very less. Why? Because you are only considering one point. You should not consider just one point. If you consider more number of points, your judgment will be more better. So in that scenario, you can use k equal to some other value other than 1. Hi Aditya. Actually, I thought I was teaching because maybe you could take the notes. I will just repeat what I taught. Hope I am audible, right? Am I audible, Aditya? Okay, good. So I'll just repeat what I was teaching all this while now. Just repeat in a very brief manner. So today we were looking at something called k nearest neighbor classifier, which is a classifier algorithm that is one of the oldest algorithm for machine learning. Okay, and to draw a k nearest neighbor classifier, so first of all you should know what is a classifier. A classifier is nothing but that outputs the set of classes, either it is 0 or 1, or let's say one problem could be if for example let us take this example where there's a graph where the x-axis denotes the age of a person and the y-axis denotes if the person has cancer or not, and the points that are labeled green are person who do not have cancer, and the points that are labeled that are red crosses are points that people have cancer. Okay, now if you look at this algorithm very carefully, and if I ask you very small thing, if let's say you take the point x1, which is a point that is written here, right? Okay, let me just write it in a better manner. So let's say this point x1, okay, and if I ask you, should it belong to the green class or should it belong to the red class by looking at the data? What will be your answer in that scenario? Can you look at the data and say that which class should x1 belong to? Is it the red class or the green class? So if you look at the data, it is very simple to say it is the green class. Why? Because you tend to make an assumption that points that are closer to x1 are the green, are the have the same label, and that is the exact assumption that k nearest neighbor does, that the data points that are close to each other tend to have the same label. So in this scenario, since the data points that are close enough, which is in this scenario, see all the green points are in a cluster, all the red points are in another cluster. So, but if you look at another example, x2, okay, x2, okay, if I ask you which, let's say this point is not there, let me remove this point, okay. Let's say if I ask you which class should it belong to, okay, your algorithm might be a bit confused here because if you just take the closest point, just one point, then maybe this is the closest as well as this is the closest, correct? Right? So if your algorithm says, then it could either output a green or a red class. But let's say if I take that, instead of considering only one point, which is the closest point, let us consider 3 points. So in that scenario, you are considering this point, you are considering this point, and you are also considering this point. Okay. You saw that these three are the closest points to x2, and two of them have a red class, right? So majority wins in this case, and you can conclude that x2 will also belong to the red class. So previously you were only looking at just 1 point. Now you are looking at 3 points. So that is only the definition of K. K means the number of points that you are considering in your analysis. Okay, which means if you are considering the nearest 3 points, then the value of K is 3. If you are considering the nearest 5 points, the value of K is 5, and so on. Okay, so then the next one is we wrote a simple algorithm on how you can uh, do this machine learning process, where what you do is, let's say you want the algorithm to predict for x, which is a data point x. You want to predict what class should it belong to. First, what you would do is you would compute the distance of x with all the points in the data set, which means I have considered a distance vector, let's call it dist, that consists of the distance of x with each point xi for all I belonging to the data set. Okay. Then I will sort the distance vector in a ascending order fashion, and then I will take the first top k elements from the distance vector, and then I will do a majority vote. So for an example, let's say that if you are considering a point like okay, so let's say you consider a point where you are considering the k, a value of k as 4. So your distance of 4 denotes the 4 closest points. And in that case, 3 points are green, 1 point is red. So what will you answer? You will do a majority vote, means you see that the greens have more number of answers. So you will answer the point as green. So this is roughly the algorithm, very simple algorithm, nothing much difficult in this, but still there are a lot of questions that they ask, I mean that has been asked during the exams about how you can solve these questions now, in interviews actually, to be particular. Now when we say distance, I was very vaguely saying something called dist of x comma xi. If you are given 2 points, okay, how can you calculate the distance between those 2 points? Do you know any algorithm to find the distance of 2 points? This is, I think you must have read it in your school. Distance between 2 points. Yeah. Is there a way to measure the distance between 2 points? How can I measure it? Okay, good. So yeah, Euclidean distance is one. Okay. Euclidean distance is definitely one of the distance metrics. But I say something called Minkowski distance. Now you might say, what is Minkowski distance, right? So what Minkowski distance is that the distance between a point x comma z is nothing but, you will consider uh, all possible dimensions of the vector x. It could be a two-dimensional vector or a three-dimensional or four-dimensional. A single dimension could be anything. And the distance formula says that it is nothing but what is the value of x for that dimension minus what is the value of z for that dimension, whole to the power p, whole to the power 1 by p. Now you might think, what is this? Correct? Okay, good. That's absolutely okay if you think that. I will tell you one thing. This is, if you consider, let's say, D as 2. Let's say it's a two-dimensional space, and let's say your value of P is also 2. Okay? Your value of D is 2, your value of P is 2, which means your distance of x comma z is nothing but x1 is nothing but x1 minus z1 whole square plus x2 minus z2 square whole to the power 1 by 2. I just expanded the formula that I wrote on the top, right? For x equal to 2, for d equal to 2 and p equal to 2. Now, have you seen this formula anywhere? X2 minus x1 whole square plus y2 minus y1 whole square root over. What is this formula? Have you ever seen this formula anywhere? Isn't this the formula of something that was already written in the chat? Euclidean distance, right? So this is nothing but Euclidean distance. Okay, fine. Now let's take p equal to 1. Okay, if you take p equal to 1, it is nothing but x. You are not taking the square, neither you are taking the roots. You are just taking the difference across different dimensions, and this is also called as Manhattan distance. So have you heard of Manhattan distance? Yes. What is Manhattan distance? Acha, what is this bars here? Is that necessary? What is that bar here? I never said what is that bar. What is that bar? That bar is nothing but the absolute value. So let's say if one dimension is positive x and some dimension is negative x, then if you do not consider the bar, then you are trying to say that distance between the two dimensions are 0. 2 points are 0, but that is not the case. So that's why what you do is you put a absolute value, which you take the positive value in that case. And since you are doing a square here, square is always positive, so that's why you will not face that distance. So if you just learn the Minkowski distance formula, you will be able to say what is the Euclidean distance, you will be able to say what is a Manhattan distance given the Euclidean formula. Okay. There is one more thing. So in machine learning, right, if you take any feature, let's say I take a feature called height, and let's say I take a feature called gender. Okay, height is, let's say, 181, 173, 178, 182, 172, and let's say gender is male, female, female, male, female. So is there any difference? So what we do is, again, let me give the answer only. The thing is, what we call this height variable is something called a continuous variable, because its domain is a set of some infinite set, like a real integers or something like that. But when it comes to gender, it is something called a categorical variable, because this variable cannot have any arbitrary value. Its value is something in a finite set. In this case, for gender, it could be either male or female. So it's a finite set of values, and that is called a categorical variable. Now, if I give you that someone is male and someone is female, and I tell you what is the distance between these 2 points, okay? What is the distance between 2 points? One is male, one is female. How will you calculate it? Can you apply the Euclidean distance formula to calculate the difference? Distance between a point that is labeled male and a point that is labeled female. Can you apply Euclidean distance? Yes? No? How? What is the value of male then? What is the answer for this one? What is the value of male? Or what is the value of female? So see, no. Okay, fine. So, okay, fine, good. Okay. Let me say you are measuring the distance between a point x comma y. Okay. And let's say it's a Manhattan distance, which means the formula is something very simple. Sigma y equal to 1 to 2, because it has two dimensions. You will say x of y minus y of, oh sorry, should not be, maybe let's take this point as z, okay, just not to be confused, z of y, the mod. Okay, let's say you will say now that, yeah, okay, fine, I will take the mod of x1 minus z1. Okay, and let's say this denotes the height, the first dimension denotes the height, plus mod of x2 minus y2. This denotes the height, x1 and z1, so you can calculate it. But can you calculate the distance between this dimension? x2 minus z2, sorry, not y2. x2 minus z2. Can you calculate for the second case as well? First thing though, okay, maybe x is the value has 180 and the value of z is 190. 180 minus 190 is minus 10. You take the absolute value, so that is 10. That's okay. But let's say one is male and another is also male. One is female, another is also female. Or one is male, one is female. How will you calculate the distance between that dimension? What can you do in that case? Okay. So one way is to do something called encoding, that you are saying perfectly fine. But let's say I don't want to do encoding as well. Okay. So what I can do is, in this scenario, I will always have to do encoding. But what other things I can do is, because why it's only encoding, let me tell you. But one thing that you can do is, there is a concept called Hamming distance. Okay. Let's take two values. One is called, let's say, my name, Aditya. Okay. And the other one, let's say, is called maybe some other name. Let's say Akash. Okay, two names are there. Okay, first thing that I will have to consider is both of these strings that I have should have the same length of characters. If you look carefully, both of them have the same length of characters. And then, sorry, and then what I do is I do a element wise comparison, and the number of elements that are not matching, that will be my Hamming distance. In this scenario, if you see, only the first letter is matching between these two, all other letters are not matching, correct? So that is why Hamming distance of this will be 5. This is one way to calculate the Hamming distance. Okay. Another way to calculate the Hamming distance would be to do encoding. In the sense, what you can do is you can say that male denotes a value 0, female denotes a value 1. Okay. And so if you have male and female, so they are opposites. So you can say the value will be 1, because 0 minus 1, the absolute is 1. 1 minus 0, the absolute is also 1. Right. But if there are two males or two females, then it will be 0, because they are the same in that dimension. Understood? Understood? Yes or no? Yes? Good. These are something very simple, right? So just remember two ways to you calculate distance. One is the Minkowski distance. Minkowski distance, if you remember the formula, then it's very easy to get the Euclidean and the Manhattan distance. I am 95% sure there will be a question on finding the distance using Minkowski distance for any value of r. So don't just learn Euclidean distance and go to the exam. That won't be the right way to do it. And for categorical, how can you measure? Might be there are questions to measure the Hamming distance. I would suggest you to go through it. And the only criteria that you can use for Hamming distance is that your length of the string should be the same. Awesome. Okay, distance metric for categorical, we already saw that. Now, when I say that, let's take any basic model now again, right? I mean, let's take plane. My voice for some reason. Let me just change my network. I'll be back in a minute. Yeah, I will be back in a minute. I think I'm dropping my network.
You are currently the only person in this conference.
Okay. Hope I'm audible. So yeah. So as I was saying, let's take another XY plane, right? Um, okay, this sometimes works, sometimes doesn't. Okay, fine. No, कोई बात नहीं. Let's just, okay, I'll try my best to draw a straight line. Yeah, I'll just try my best to draw a straight line. Yeah, okay. So let's again draw some set of points. Let's say that in some process, okay, some set of data points. Okay, let's say that my test point is this one. Okay, let's say my test point is the black one, black color. Which class should it belong to? it should belong to green, right? We just looked at that, right? The algorithm. Let's say that the algorithm you have designed such a manner that it kind of predicts that no, it is a cross. Okay. So is this a prediction wrong? Most likely it is wrong if you are going with the assumption. So how can you quantify whether something is wrong or right? The most important concept in the entire machine learning is this only. So something called loss function. Loss function, or it is also called an error function, are used to gauge the error, that is, the measure the error between the output that your model has predicted and what is the value of the actual value of the variable. Okay, a loss function can determine how the model is performing by comparing the distance between the prediction output and the target values. If you have a smaller loss function in your data set, that means the model is performing better and in yielding predictions that are closer to the what you want. So what it means is, so let's say you have trained your model is ready, okay, and you have something called a validation set. Validation set is used to test the efficacy of your model. You cannot use the test set here because test set you can only use it once. That is the time when you are trying to finally evaluate the model. So let's say you have a data set of validation. You feed it to the model, whatever model you have built, and the model outputs you some predictions. Let's call it ypred, which denotes the predictions if you input the validation data set dval into the model. Okay. I say one loss function could be this. So the loss function for a point ypred and given its true value, that is y true, is nothing but something called delta of ypred is not equal to y true. Now you might think, what is this? Hold on for a second, it's very simple. Delta function, delta of x is 1 if x is true and is 0 if x is false. Okay? And the loss function for the data set dval on the given hypothesis H will be the summation of all the points in the validation data set. Let's call it nval. Okay. Delta of what do you predict for those nvals, yip, minus what is the true value of that ith prediction, which also means delta of y, or let me do it this way. I can use this function on the top. Sum of loss yi pred comma yi true. So what it will do is, you have built your model. Your model, let's say, your validation set consists of 5 observations. Okay, let's say this is x1, x2, x3, x4, x5. Okay, and let's say your y true for the model, which is for each of these x's, was the true value of them were, let's say, 0, 1, 1, 0, 1. Just a simple example I have written. And your model has predicted that this is 0, this is 0, this is 1, this is 0, this is 0. This is your data set. You had set of points x1 till x5. The true value of y was given to you, which is given, and your model has predicted that the following values. Now, if I ask you what is the loss of this data set, what is the loss value for this t-val, right? This is nothing but how many of these data points are there where the y true does not match the y pred, which means if the true value is 0 and your model has predicted 0, or if the true value is 1 and your model has predicted 1, that means the model is correct, right? Whatever model you designed is perfectly okay. But if the true value is 1 and you predict 0, or if it is 0 and 1, then that is a misprediction. And this delta function says what is the predicted value, and if it is not equal to the true value, then it is 1. Okay, or else it's 0. So if you calculate in this scenario, you will get the number of mispredictions as 2, because what are the mispredictions? One is x2, you predicted 0 when it should have been 1. Another is x5, when you predicted 0 and it should have been 1. Okay, and there are optimizer algorithms designed to minimize this loss function. We will go to that later on. There are many more loss functions in the literature. We will go step by step as we learn the models. Today, since we talked about this one, this loss function is called 0-1 loss. And please, for heaven's sake, read this and go to the exam. I have a huge hunch that they will ask a question on this. Okay, please make sure you know this, or else it's a nightmare to sit in the exam, because it will be very difficult or else. Okay, it's a very simple thing, right? Very, very simple loss. Okay, if you need another example, let me know. We can do some example as well. So let's do one thing. Let's do one small example here. Okay, let's do it here. Okay, let's say this is your x, this is the y true, and this is the y pred. Okay, x denotes some set of data points. Let's take a one-dimensional data point where it is d1, d2, d3, d4, d5, d6, 6 data points, let's say. Y true is 2, 1, 0, 1, 0, 1. Okay, your model predicted this as 2, this also as 2, this as 1, this as 1, this as 0, this as 0. What is your 0-1 loss? Take 1 minute to answer it. What is the 0-1 loss? You just have to count the mispredictions. How many data points are there where you should have had a value of x, but you got a value y, where x is not equal to y. Just that's it. So come on, it should be very simple. Won't even take 30 seconds to be honest. So what is a 0-1 loss? If there are three mispredictions, misvalues, three only, right? So 0-1 loss denotes how many mispredictions you have. Since you have three misvalues, what are those three misvalues, Sahil? Which data points? One is D2, another D2, D3, D6, right? D2, D3, D6. Yeah, these three data points have misvalues. So a 0-1 loss will be 3. Let me do one small thing, okay? And again, this is not part of the slides. I will change it later on. Let's say I change this one to a, instead of a not equal to, I change it to an equal to equal to. Can you tell me what is this called? And let's say, for example, let's say this is the new delta function I have, and I divide it by the total number of samples I have. Let's say it is capital N. Okay. What do you think I'm trying to calculate here? Think. Miss rate, sure. Let me give you a hint. Your model has predicted that out of 10 samples, 5 are correct. And this metric gave something called 50%. What is 50%? 5 by 10, 0.5. What is 0.5? Accuracy, right? It's the accuracy of your model. And do you want to minimize your accuracy or maximize your accuracy? That's obvious, right? You would want to maximize your accuracy. So that's why loss functions are some functions where you always try to decrease the value. Okay. And this thing is a part of your evaluation of the model. Finally, when you want to evaluate your model, if you want to give it to the customer, you want to tell him that you won't tell na that, oh, this model has a 0 1 loss of 100. We will say what is 0 1 loss, right? Something that the customers know better is something called accuracy. That's why accuracy is something called a model metric. It's not a loss function. Okay. Then you will, but if you tell me that, hey, this is the model and its accuracy is 98%, then I know, right? Then I know that out of 100 predictions, 98 are correct, right? So make sure that you're aware of this distinction as well. Okay. Huh. Now we looked at classifier models where a simple example of a classifier model. I have not finished classifier yet because that's another new ball game in itself. There are some more classifier models we will study later on. What we studied till now was, oh, there's a free space here. So what we studied till now was something called classification model, where you have a set of data points and you predict the value y, and the y is nothing but a set of values 0, 1, 2, dot, 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 something like this. Okay, 0, 1, 2, dot, 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 till some k or some c. Let's call it c. If the value of c is 2, that is called a binary classification. You're trying to predict out of two classes. It could be extended to any C. C could be anything. It could be a 3 class or 4 class or 5 class. There are different examples present. For example, if you want to predict that X denotes the marks in different subjects, Y could denote whether the person is fail or pass. This is a binary classification problem. Another thing could be that given this set of points, let's say there is a particular subject where you have scored, it has three sections. You have scored some marks in section A, some marks in section B, some marks in section C. Now your output could be whether the person gets a grade or a B grade or a C grade or a D grade or an F grade. So in this case, your number of classes will be 5. Okay, but sometimes what can happen is, so let's look at an example. So if you look at this example, okay, this has been taken from a website. I will have to quote that. That's called Analytics Vidya. Thank you for giving this website. I'll quote them here. Give due credits to the people who have designed it. Let me first explain the data set. The data set consists of IDs, where ID denotes just a unique number. Height, where height denotes the height of an individual. 5, 5.1, 5.6 are different heights in some scale. Okay, let's not worry about the scale. Okay. The age denotes the age of the person, and the weight denotes the what is the weight of that person. Okay. Now, if you look carefully here, for ID 11, we wish to find out what is the weight of that person. Okay. And unlike the previous scenarios, weight can be any value across a different range of integer. Let's call it Z. and obviously z plus, right? Someone cannot have a negative weight or zero. Z plus denotes all the positive integers. So let's denote that it comes from z plus. So this is called a regression problem because your output y is a continuous variable. Okay. Let's say I want to calculate what is the weight of the person with ID 11. Okay. Given this height and age and all, how will you do that? First thing is you draw a graph. This is your graph of the different data points that are present, right? Now you wish to calculate, this is your ID 11 if you can't see, okay, because of the color. This is your ID 11. You want to calculate the weight of this person. If I give you one simple algorithm, what you can do is, you see ID 11, okay, take its nearest three neighbors. Let's take K as 3, okay. Let's take the value of its three nearest neighbors. So you would take the value of this, and of this, which is the person with weight ID 5, ID 1, and ID 6. And you collect the weights of all these three people and average them. Understood? You want to calculate the weight of a person with ID 11. Let's take the value of K as 3. I fixed it now. You can do anything you want, but for now, let's take the value of K as 3. You look at the three closest points. It's the same as K nearest neighbor classifier we saw earlier. But those three nearest points to the point with ID 11, you take an average of the weights of those points. So what is the average of the weight of the points? It will be 77 plus 72 plus, I guess, 60 by 3. And that will be the weight of the person with ID 11 that your model will predict. If the model predicts it correctly or incorrectly, that's a different question. But this is what the K nearest neighbor regressor algorithm will compute. Okay. So if the K value of K is 3, then the Y11 or the weight of the person with ID 11 will be one third of the weight of person with ID 1, weight of person with ID 5, and the weight of person with ID 6. And whatever is the value, I think it is 69.67, I guess. You can do the calculation, but this is what I think is the answer. Okay, this is one algorithm. So this is called nothing but K nearest neighbor regressor. The algorithm is something very simple. Again, let me write the algorithm. What you first do is you compute the distance of the test point X with all points in the data set. Okay, let's call it some vector dist. Number two is you sort the vector dist in ascending order. So in that case, the point with the smallest distance will be at the top. And in the third point, take the top k distances. So dist k denotes the top k values from the dist array. And finally, your ypred is nothing but 1 by k summation of I equal to 1 to k. What is the corresponding y value of the given test point? Okay, very simple algorithm. Now the question lies, how will you compute the loss function? Okay, 0, 1 loss you can't do here because there is no 0, 1 here. It could contain any value from any set of integers. How will you calculate the loss? To do that, take something very simple, okay? Let's take a graph, very simple graph, and let's say that with green I denote this point x, okay? Let's say the value of it is 72. And whatever model you made for this same data point, the model predicted a value. Uh, model predicted a value. Let's say this is what the model predicted, a value 60. Okay, model predicted value 60. You want to measure how off are you with the true value. How can you do that? What are the ways you can do to measure how off are you from the true value? Is there any way you can quantify it? Is what I'm asking. Yes. If I tell you that the value is 12, then what am I doing? I will tell you the value. I think the value is 12. What am I doing exactly? Okay. So one loss function that we can talk about is something called the mean squared error. So this is the, well, let me take the next slide only. It's fine. One loss function that we know is something called the squared error loss. Okay? Which means the squared error loss for a point y and its prediction, let's call it y cap, is nothing but y minus y cap whole square. So if the value of y is 72 and your model predicted 60, what is your squared loss? Can you calculate just to see if you guys are attentive? What is the squared loss in this scenario? 144, right? Something very simple. And across, this is for a single data point, right? Across a data set D, your squared loss will be 1 by n, where n denotes the number of samples in your data set, loss of yi comma yi hat. And if you look carefully in this formula, you are doing something called taking the average, right? 1 by n denotes you are summing up all the losses across each point, and then you are taking the average. And this is a very famous, very important loss function called mean squared error loss, or MSE. Okay, very important, guys. Please, if you don't know this, don't sit for the exam. It's that simple. Okay. The second loss function we have is something called a absolute error loss. The absolute error loss of 2 points y comma y cap is nothing but the absolute difference between the two loss. So again, quickly, what do you think will be the value for the example? What is the absolute error loss for the example I have told here? 12. Perfect. So the for it will be 12. And across a data set D, the formula is absolutely the same. No difference at all. I equal to 1 to n, the loss of yi, comma, yi cap. And this one is again, you are taking the mean of it. Your loss function has changed. Okay. This is called MAE, or mean absolute error. Now, let me ask you a very basic question. Okay, this is a maths question. This is not a machine learning question today. Okay, let's say this is Aditya loss function or Aditya error. Okay, my name Aditya error. Okay. Oh, whoa. How did it zoomed in so much? Do you guys see something zoomed in so much? Yeah, I mean, okay. Ah, okay. Even I think the black whiteboard cried seeing what I'm going to write now, but okay. This is what you to teach only. Okay. Yeah, thanks. Sorry. So, Aditya error means the loss of a point y and y is y minus y hat. Can this be a loss function? If no, why? Don't just say no. Negative loss? What is the problem? For that, it is 12, na, still. Aditya error of the example that I gave is 12. So, where is the negative part? What is the issue with this loss function? Think, it's mathematical question. Can you, I'll give you a hint. Can you make mistakes and still get a loss of 0? Hmm. Error will cancel out. Very good. Very good. So, for example, if this is your true value, let's say this is a line. One point is predicted here, so it has a distance d. Another point is predicted here, which has another distance minus d. And if you add them, let's say one point was y equal to 72, your prediction was 60. Another point was, let's say, y equal to 60, your prediction was 48. So, or sorry, your prediction was 72. So in that case, 12 minus 12 becomes 0. So your loss is 0. That is not correct. So how do you solve them? How do you solve the problem, Aditya error? You use the first two functions, right? That's why it was written. That's why it was written, right? That's why you take the absolute value or you take the square. Okay, so good, nice. Aditya error is something that is not present and hope you understand now why. Huh. Next question. Again, mathematical. Okay, I'm not teaching you machine learning, mathematics. Okay, is it a choice or is it okay for me to use any function anytime? What I mean is there some provision where I can possibly use a squared error and not an absolute error, or where a position where I should use an absolute error but not a squared error? Understood the question? Can I use them anytime, anywhere? मेरा मन किया I will use squared error. मेरा मन किया I will use absolute error. Is it like that, or there are some scenarios where squared error is better, absolute error is sometimes better? Can you think of it? Mathematics again. This is not machine learning. Mathematics. Yes, think. I won't answer for at least 2 minutes now because I want you guys to think. This is very mathematical. If you need a hint, I can give that for sure, but think. Criteria. For example, what do you mean by criteria? Let's take an example, okay? Let's take a line, okay? Okay, let's say this is your data set and this is your line that your machine learning model predicted, made this line. We use MSE for differential functions. Okay, okay. Okay, fine. Now tell me one very basic question I have. X, y equal to x square. Okay. Is this function a linear function or an exponential function? It's an exponential function, right? If the difference between the true value and the predicted value is huge, let's take let's say that this oops, something really weird. Okay. Huh. So let's say that the model predicted, so this is your line that your model has drawn. Okay. And let's say one of the data points is this. So the error is this. Huh. Which will be more, the squared error or the absolute error? What will happen to the squared error if I do d square? The value of d is huge. Squared error will be huge. It will blow up, right? It might just dominate all the other errors you see, right? So that is the only difference between squared error and absolute error. Squared error is not robust to outliers because this point that I drew here is an outlier because it doesn't follow the pattern. The pattern is a straight line, it's a very linear relationship I can see. Only one point is off, that's okay, right? That's why this is also called an outlier. And because of this outlier was present, your value, that is D, is huge. And that's why it might also dominate. So what the model will say here is, your loss function will say, just because of one single point, your model will have a huge loss function. But if you look carefully, the model is more than perfect, right? Because you are able to predict the values correctly for the other points, right? But the absolute error will be much, much less here because you're not taking a square or something. And that is why you will use an absolute error when your model is susceptible or to outliers. If you have outliers in your data set, you should use an absolute error. So you might think now that we should always use an absolute error, right? No. So what happens is, again, you might not know this also, that's okay. So if you take the loss function, right? If you take the loss function, let's say a mean squared error, your graph will look something like this. Something like this. Across different model iterations, your graph will look something like this. And this here, this point here denotes the point where your loss is the minimum. And this is called the global minima because if you have something like this, if your loss graph is something like, okay, I'm not drawing the Indian flag, just giving an example. In that scenario, if you see, if you let's say reach here, or let's say reach here, then these are also minima, but these are called local minima because your global minima is somewhere over here. Okay, because those are not your minimum loss is somewhere here, but your optimizer will tell you that, hey, this is the minimum, or that is the minimum, this either this one or this one could be one of the answers by the local minima or the algorithm, but this one will be the global part. Okay, understood this part? So let me give you the good part. Let me give you the good news here. Squared error loss is a quadratic function, and a quadratic function has a property that it is always convex, which means a quadratic function will never have these local minimas, but an absolute error can have these local minimas as well. So that is why people use the squared error loss. Okay. Now, why it is convex? Again, that is not part of the syllabus. Even I forgot that reasoning. That I read it long back when I was in my masters. That quadratic functions are convex in nature. That is why your model will always have a global minima. And for outliers, you can do some outlier treatment. There are treatment that that you can use for outliers. There's something called box plots and all that are not there in your syllabus. That will form in your data pre-processing step. Okay, but that is not in your syllabus, so let's not talk about it. Okay, but here is something else. So there was this genius called Huber. What Huber did was he came up with a loss function called Huber loss. And what Huber tried to do was he combined the squared error and the absolute error. So what he did was the loss of two variables y comma y prime is nothing but y minus y hat whole square if y minus y hat is less than or equal to some delta, or else it is the absolute error loss multiplied by delta minus 1 by 2 delta square if sorry delta square otherwise. Okay, let me repeat once again. This delta is a hyperparameter, which means a parameter that you will have to set on your own. And if the difference between two data points is less than the delta, then the square won't blow up. Then you can take the square, or else you will just use the linear equation on the bottom, which is just take the absolute difference, multiply by delta minus half of delta square. Okay, this is called the Huber loss. Okay, I think we already discussed this loss functions in regression. So let's not go to cross validation for now. I have some questions for on k nearest neighbors. Let's try to tackle that. So again, before actually going into it, I have to teach you another small thing in this. So if you remember, if you have watched my first lecture, I told you that typically a machine learning model takes in a data, takes in an output, and it gives you a function that you can use to do the testing. By any chance, till now, did I ever tell you the function f? Or is there a function f for k nearest neighbor? It's just very simple, right? You look at the data set, and then by looking at the data set available, you try to do the prediction straight away. You do not actually go ahead and train a model, find the coefficients, and then use it for testing. You actually are not doing that, right? You just look at the data set, plot the point, see the distance, nearest point, and that's it, right? You're not actually creating a model in this scenario. So your training time is nothing. Everything you are doing in the test time only. There's no model you are creating in this case. You're just looking at the data set and finding out the correct value. So that is actually the first question. The first question says KNN does more computation on test time rather than train time, which is true because you're not actually creating any model. Okay, there is no training time. Yeah, how about this one? What do you think is the best value of k according to this graph? The x-axis denotes the value of different k. Data scientist is trying to find out for different k what is the value, and the error rate denotes the y-axis. So y-axis denotes the error rate, and the graph denotes the validation error. Okay, so you train the model, you look at the valid. So you have the data set, you use the validation set to calculate the different predictions and the error, and this is the graph you get. Absolutely. So if you look at the graph for b equal to 10, your loss is the minimum. So that's why you can take k value of k as 10. Okay. So I have not actually taught you this thing that much. Which of the following distance metric cannot be used because it was not there in syllabus. Okay, this was just I think I had maybe okay. So Tanimoto and Jacquard and Mahalanobis distance are also distances that are available. Minkowski we already studied. Manhattan we already studied. Others are also some variations of by if you vary the value of p in Minkowski distance, you will get all. So you can use actually all of them. Okay. Yeah. Which of the following option is true about KNN algorithm? It can be used for classification, it can be used for regression, it can be used for both classification as well as regression problems. Very straightforward. We looked at KNN classifier, we looked at KNN regressor, right? So C, both. Okay, this is annoying. Okay. Apparently it doesn't happen in my iPad only when I see it. Okay. What is the Euclidean distance between these two data points A and B? Sure. One or two, sure. Sure, answer is two. No problem, no problem. Yeah, so how will you calculate Euclidean distance? Okay, back to elementary maths. D of A comma B is nothing but root over x2 minus x1 whole square plus y2 minus y1 whole square. So 2 minus 1 whole square plus 3 minus 3 whole square, which is 1 square, which is 1. You take the absolute value, distance can never be negative, right? So it is 1, and that's why the answer is 1. Okay. Yeah. Perfect. Perfect. Yeah. Good. What do you think is the Manhattan distance between these 2 points? Again, something very simple. D A comma B is nothing but the absolute value of 2 minus 1 plus 3 minus 3. No squares, no root overs. So we have 1. Simple. Hmm. How much time will be taken if you are using 1 NN versus 2 NN versus 3 NN? Let's say you have a data point X and you use it on three models. One is a 1 NN, one is a 2 NN, one is a 3 NN. What will be the time taken by 1 NN, 2 NN, and 3 NN? Which one will take the most amount of time? Sahil is saying B. So 3 NN, let me give you a hint, Aditya. Instead of looking at just one point, now you decide that one is not enough for me. So I looked at 2 points, which is 2 NN. And someone else said, no, even 2 is not enough. I will look at 3 NN, which is 3 points. How much time will it take you to make a decision if you are looking at only 1 point compared to looking at 3 points? If you want to know what college will I get in after the gate, if you ask one person and take an opinion, is it faster than asking two people or asking three people compared to just asking one person and getting the answer? Right? So 3NN will take the most amount of time because you are looking at 3 points. 2NN will take somewhat lesser. 1NN will take the least amount of time. You just looked at 1 point. So that's why B is the correct answer. Okay. Okay. Now let's come back to a very, 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 very important topic: cross validation. Okay. Cross validation. Okay. First, let us see where does even validation comes from. I think I explained it in the previous class, but still for a recap. Let's take this as your data set. This is your entire data set. You divide this data set into three different parts. Something we call the test set, something we call the training set, and something we call what? The validation set. Okay. The training set you use to train the model. In this scenario, in this case, in KNN, the training set will be used to plot your graph. That graph you draw, right, to do the prediction. The validation set is something that you know the true output of, but that your model has not seen it. So you will use it to test your model, whether your model is working fine or not. You will compute the loss and so on. And the test set is a test data set that you can only use it once. You need to use it once and throw it away. You can't reuse it. You can't retrain on the test set. Okay. This is more like training set denotes you watching the lectures for the GATE exam. Validation set denotes the PYQs. If you answer it correctly, you are doing good. If you're not, then your training set has to be better. In that case, you will have to train your model a bit more, learn more lectures or watch more videos or read some books. And then your test set denotes the GATE exam. Certainly in the GATE exam, you only give it once per year at least. So now cross validation means, so if I, let's say, have some data points from x1 till x100. Okay. Let's say that from x90 till x100, you have designated these points as your test set. Okay. Let's say from points x1 till x60 denote your training set. And let's say your point x61 till x89, they all denote your validation set. Okay. So you train your model on the points x1 till x60. You test it on, you validate your model if it is running okay on x61 till x89, and you test your model on x90 till x100. Okay. Right. Now, here is the question. If you evaluate your model on x1 till x60, sorry, if you train your model in x1 and x60, can you be sure, can you surely tell me that your x61 till x89, the data points present here in the validation set, will actually don't have any overlap with the training set? What do I mean by it is, let's say that x1 till x60, the values that are present, somehow x61 till x89 also, the same values are present. Okay. Which means when you trained your model, which means when you watch the lectures, somehow I taught you all the PYQs of GATE. Okay, so you have trained your model saying these are the PYQs, this is how I have to solve, and this will be the answer. And your validation set is the PYQ itself. Now tell me, what will be your validation error? Zero, right? Because you trained your model using the PYQs, and then when you are going and solving the same PYQ again, you see that, oh, this is something I've already seen. So that is when I call overlap, right? Now, what can you do better? Let me give you another small hint. Okay. So again, let me be clarify this one. I think this will be x91 till x100, the 10 data points, and this will be till x90, 61 till 90. Okay. So these are 90 data points, correct? Okay. From x1 till x90. Okay. Let me give you one small thing that I can do. Let me give you a small algorithm. Let's say that this is your training set, this is your validation set, and this is your error. Instead of pre-setting that only x61 till x90 will be the part of your validation set, let's say that x1 till x30. Oh, okay. So, okay, one more criteria that you have to put is okay, sorry. Okay. So one more criteria that you have to put is your training set should always contain 60 data points. Okay. So initially you would say that let's put x1 to x60 as a training set and 61 to 90 as the test set, and this will give you one error. Let's call it E1. Okay. Let's say that another data set could be from x31 till x90 forms your training set, and 1 till 30 forms your validation set. And with this, you evaluate your validation error and you get E2. So this is your validation error, you got E2. And another thing that you can do is 1 to 30 and 61 to 90 form your training set, and 31 till 60 forms your validation set, and you get an error E3. And I will average this out and get my error E. Understood what I'm doing? I'm trying to divide the data set in 3 by sets of 30. In the sense, first case, my validation set will contain all points from x61 till x90. So the remaining x1 till x60 are the training set. Next part is validation contains x1 till x30 and 31 to 90 is the training set. And the next part is the same. Okay, I mean 31 to 60 is my validation set, and 1 to 30, 61 to 90 forms my training set. I compute their individual validation errors E1, E2, E3, and I average them out to calculate the final error, that is E. First of all, let me ask you the very basic question. Is it better than the earlier scenario? Yes, I mean you're now validating your data across each different point. If you look carefully, initially your model does not know 61 to 90. So all these three are three different models also. Okay, so 61 to 90 didn't knew, so you tried to create the model using 1 to 60. Second time it didn't know 1 to 30, so you tried to create using 31 to 90. And the third time it didn't know 31 to 60, and you could find you made a model using the other points. This is better than the previous one, correct? What is the disadvantage? Aren't you taking more time to train your model now? Because this one you trained a model, this one you trained a model, this one you trained a model, and this is for this is for 3 sets. Let's say I tell you that the validation set should contain 15 data points only. Then you will have 6 different set of models, right? If your validation set contains only 15 data points. Now, first of all, There is a concept called k-fold cross-validation, where the amount of k, where k denotes the number of validation sets you will create. Okay, which means for the previous example, value of k was 3. That's why each validation set consisted of 30 data points. There were 90 in total. You said k is 3, so divide them in chunks of 3. So it is 30 per set. If let's say the value of k is 6, then the dval is 15 per data set, correct? And then your more the value of k, you will have more number of data sets, correct? But here is one another small thing that I want to say. Let's say that the value of k is n minus 1, which means if you have a data set from x1 till x100, let's say, first what you do is you leave x1 out, train your model on x2 till x100, and report the loss on x1. Second time, you use x1 in your training set, you leave x2 out. This is your x2. So initially you left x1 out. Now you consider x1, you leave x2 out and consider the remaining points from x3 till x100 and train a model and compute the loss on x2. Then the next time what you do is you consider x1 and x2 both, but exclude x3 and compute the loss on x3. And similarly, you do it for all the 100 data points. So sorry, not n minus 1, should be. Okay. I mean, if the 100 data points, you will have 100 different models. Each model has its own error, and then you average out the error. Now, if you see carefully, each training set in any of the model is a maximum, right? Considering anything else, like you are just leaving one out. I mean, that's the name actually of the algorithm, leave one out cross validation. So you're leaving one point out and considering the remaining n minus 1 points to create your model. You have the most amount of points, your model will be good, but then you are only considering 1 point. So what is the issue with this approach? You're having the most amount of data points in your training set, that I agree with, and your model will be much better in this scenario. Right, you will only test on 1 point. So in the first scenario, okay, let me just draw some cases, okay? So this is your D test, this is your D train, and this is your error. So initially your test contains x1, your train contains x2 till x100, and your error is even. Now you have x1 union x3 till x100. Oh, sorry. This is your training set actually. Just a second. Yeah. So this is your training set. You will consider x2, x3, and all points that are not x2 or x3. I mean, this will contains all xi where I is not 2, you e2, all xi where I is not 3, e3, and so on. Yeah, overfitting could be an issue, correct? What is the biggest problem? I told you earlier that when you had k equal to 3, you were creating 3 different models and testing them out. Let's say your data set contains of 1 crore samples. What is the problem then? You will create 1 crore models, right? And one model creation takes a hell lot of time, right? So that is why it is not a perfect way to do it, but this is also one of the ways to do it. Okay, just for the syllabus I taught, and that is called leave one out cross validation. Okay, leave one out cross validation. So if you don't consider cross validation, then your value of k is 1. You're only considering one validation set, right? Now k, uh, then that means you are considering n validation sets, which is nothing but leave one out cross validation. Okay, fine. Okay. The last topic that we will discuss for today is k nearest neighbors for multi-class classification. What is this? First of all, I already explained you guys what is multi-class, right? Instead of, let's say, two classes, which is a binary classification, it will contain multi-classes. And the question is, if you look carefully, right, none of my algorithms will change. In the sense, let's look at the KNN classifier and let's draw a simple data set again. Okay. Let's take green points. Let's take blue points, denotes one class. Let's take red points. Okay, fine. Okay, let's say I want to predict what is the class for this data point, the data point labeled black. Okay, and let's say the value of k is 5. What will you answer? Is it blue, green, or red? Blue, green, or red? Blue, right? I mean, looks very simple, right? So again, none of the algorithm changes for multi-class. You can use the same algorithm. What you would do is you would calculate the distance of the point with every point in this case, and then you will try to find out that which is the nearest, which is the top k. You'll do a majority vote of the 5 nearest neighbors. Yeah, k nearest neighbors, correct. Okay, okay. So none of the algorithms change. One last point before we end this lecture is, let me give you a very simple example. So I wrote it earlier in one slide, but I wrote other things there. So I will just erase this out. For imputation, because this is important. What is imputation? So let's take a data set. Okay. Might sound weird, but still, please bear with me. It is age, sorry, this is weight, and this is your y. Okay, let's take a binary classification only. Y is, let's say, some values 0, 1, 1, 0, 1, 0, 0. Age is 23, 24, 26, 18, 17, 16, 15. Okay, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Okay, weight is 67, 71, 68, not given, 82, 90, 54. Okay, just some basic values. Okay, what do you want to predict? You want to predict y. If you look carefully, there is one data point which does not have a feature, right? This is the data point where you do not know the weight of it. But what you want to predict the y, you don't want to predict the weight, right? Now, one thing is you have to fill this missing values. And filling this missing value is something called imputation. Okay, imputation is nothing but how will you fill the missing value. Okay, one thing that you could do is you can draw a graph, okay, where your x-axis denotes the age and the y-axis denotes the weight. You can plot these data points, something like this. Okay, okay, and let's say your y denoting the y 0, you could say one color like red, and y 1 you would say one color as green. For this point which does not have a value, let's say that age is 18. Okay, you want to predict the value of 18. What is the weight for 18? Okay, I mean, you want to know the value. You don't want to predict, you want to predict y. At the end you are building a model, but in the data set only, training data set only, you do not have the value of weight for the age, for the person with age 18. One thing is to just drop off the data. I mean, just delete that data. That will solve the problem. But another thing is you can fill that missing value. Here, what we say is you can use something called KNN to do this. How? Let's take the value of k as 3 again. So for this data point, I'm just placing it arbitrarily in this plane anywhere, okay, in this Cartesian plane, okay. I could place it here as well. I could place it here as well. Anywhere I can place, I'm just placing it here, okay. Fine. I look at the 3 nearest neighbor and I take their average, okay. Let's take their average as some value, let's say 63, okay. And I can replace that value with 63. And once I know the value 63, then I can, again, this model I can draw, and then my KNN algorithm will be able to predict it for the test set. Understood how you can use imputation, how you can use KNN for doing imputation? Yeah? Any questions? Yes, please, Sahil. Just ask straight away, man.
Hi, so for distance, do we calculate the age or the weight? Because for 18, we didn't know the weight, right? So, uh, do we take 17, 16, 15 as the nearest 3 points? And that is just
Good, good, very good. So you calculate the distance between, good, very good point actually. And this is something that even I missed. Okay, okay, fine, fine, fine. I understood what you're trying to say. So what you do is the thing that you know, in this case, you know what? You know the age, right? You will only consider the age and try to find the nearest 3 points from the age. Okay? Because you don't know
yeah.
the weight, right? You need to estimate the weight. So in this scenario, the person with age 18, the nearest 3 points are person with age 17, 16, and I guess so 15, right? Obviously. And then you take their corresponding weights, take the average, and plug in the value for this data point.
Got it. Thanks.
Okay, and then you can just draw. Correct. Actually, this is what I was wanting to say. Yeah, correct. That's a very good point. Good, Sai. Very good. So again, so they might ask a question that can you use KNN for imputation? If yes, how? They can give a sample data set and ask you what is the missing value according to KNN. I hope it's very simple to answer if you look at this explanation, right? Okay, so I don't want to go into softmax because it's just a very a topic that is better understood if you have a model supporting it. So we will look at another machine learning model in the next class, which is naive Bayes classifier. And naive Bayes classifier, if we learn that, we will learn another very important, very important concept called bias variance trade-off. I'm just rushing the lectures a bit more. I'm not talking very deep into anything because of time constraints. You have less time for the gate, right? But still, I will make sure that you at least have some idea before you go to the exam, rather than it's better than zero anyway, much better than zero, that I can guarantee you. So yeah, that's it. And if you guys have any questions, feel free to stay back. Maybe